Hello and welcome to this screencast. In this screencast I'm going to show you how to do a linear regression using Solver. The method we'll use is a least squares minimization. The data that I have here is from carbon monoxide. It's a data set that we've seen before. I've already assigned the initial and final quantum numbers to this absorption rotational spectrum, and I've calculated the independent variables 2 into j plus 1 and minus 4 into j plus 1 cubed. Each of these independent variables are associated with the rotational constant and the centrifugal distortion constant. In a least squares minimization, one needs to have an initial trial guess of the values of B and D. Well, I know that if this is indeed the transition from j equals 0 to j equals 1, it occurs at approximately 2b. So if this is approximately 4, I could estimate b as being equal to 2, and I'll report that value in cell B5 there. For the centrifugal distortion constant, I can assume that to a good approximation it's equal to 0. Right, now that I have estimates for the values of B and D, I can calculate a model value for the spectral line frequencies for each of the transitions. So in column G, I'm going to calculate what the model suggests the answer should be, and that equation is given here. So it's going to be equal to B, and I'll just protect that and multiply it by 2 into j plus 1, and then add on D protected multiplied by minus 4 into j plus 1 cubed, like so. I can now autocomplete for each of the spectral lines. Of course, you can see that my guesses of B and D are not particularly accurate. They differ significantly from these observed values. Now, by hand, of course, I could try to make changes to make this agreement better. However, instead, what I'm going to do is calculate the difference between these numbers, or rather the square of the difference between these numbers, the residual, and sum up the sum of the squares of these residuals. So in column J here, let's calculate the square of the residual between the observed and the model estimate. So this will be equal to, open bracket, observed minus model, close bracket, and then I square it. I can autocomplete, and then finally, in this square here, I'm going to sum up all of these squares of the residuals. The key word I'm using is sum. Then I just highlight the cells I want to sum together. And that gives me a value of 9.43, as you can see here, given the estimates of B and D. What Solver enables us to do is minimize a particular value by changing certain parameters. And that's what I'm going to do here. So let's go to the Data tab, click on Solver, and highlight the cell, which is J13, which has already been inputted. I want it to minimize. Okay, I think normally the maximize would be checked, so you'll have to change that to minimize. And as you can see, I'm asking it to change cells B5 and B6. And now all I need to do is press solve, like so. And the values of B and D are now 1.922, 5283, and 6.1195 times 10 to the minus 6. And you can see that this does give us incredibly accurate values for each of the observed spectral lines. The only downside, of course, of using Solver to do this kind of linear regression is that it has not given us an estimate of the value of the uncertainty in both of these two parameters. But if that is not important, or you have a problem that is non-linear as opposed to linear, then Solver is a method of choice for doing these kind of calculations. Very easy to set up and very easy to treat any similar data. With regard to homework assignment 3, this method can be used to determine the temperature from the intensity data of the fundamental band. Thanks for listening.